Hi and hello. This is High Physics YouTube channel. In my previous video, we discussed about the heating effect of the electric current. For those who missed that video, the link pops up here and the link is also given in the description box below. In this video, we are going to discuss electric current and its effects. Here we are going to discuss what you mean by the magnetic effect of the electric current, that is electromagnetism. What is an electromagnet? What is a solenoid? How to use the right hand thumb rule to determine the direction of the current and uses of electromagnets. Magnetic effect of electric current. A Danish physicist Hans Christian Ørsted did an experiment in 1820. He passed a current through a wire and found that the magnetic compass needle nearby it deflected. For example, in the figure above, we have an electric wire connected to a switch. The switch is in the open position. Here you have a magnetic compass needle. Since the switch is in the open position, no current flows through the wire. As a result, there is no deflection in the magnetic needle. When the switch is closed, now the current flows through the wire. As a result, the magnetic needle which is kept nearby the wire gets deflected. This clearly shows that the current flows through the wire creates a magnetic field around it. Since we know that the magnetic needle will be deflected only in the presence of a magnetic field. This is a major discovery, as this paved way for a new branch of physics called as electromagnetism, which means that the electricity produces magnetism. Electric current produces magnetism. Before that, it was thought that the electricity and magnetism was two different phenomena. But after this experiment in 1820, electric field can create magnetism was unveiled to the world. Magnetic effect of the electric current. Here you have a wire. As shown in this diagram, here you have a wire and current flows in this direction. Around the wire, different magnetic needles or the compass needles are placed and they are deflected as shown in the figure. Which means that the current flowing through the wire in this direction produces a magnetic field in a concentric circular fashion around the wire, as shown in the diagram on the right. You have concentric circles around the wire, right? This is the magnetic field. The concentric circles are closely packed near the wire and it is widely packed. That is, the distance between the concentric circles increases as we move away from the wire, which shows that the magnetic field is very strong near the wire. Hence, the concentric circles are closely packed. Whereas, as we move away from the wire, the magnetic field gets weaker and weaker. And the magnetic field is also proportional to the amount of the current that is flowing through the wire. If we increase the current that is flowing through the wire, the magnetic field also increases. Now, how to find out the direction of the magnetic field produced around a current carrying wire? This is given by the Fleming's right hand thumb rule. Here we have to use only our right hand. Suppose if our thumb of our right hand points in the direction of the conventional current flow, that is the I direction, then all the curling fingers will point towards the direction of the magnetic field produced around the wire. So if the thumb is in the direction of the current and all the rest of the curled fingers will indicate the direction of the magnetic field as shown in the diagram. Now we see what is meant by an electromagnet. We can produce magnetism by passing an electric current, right? An electromagnet is a device that acts like a magnet when an electric current is passed through it. Here you have a horseshoe electromagnet, right? Here you have an iron core over which wire is wound and the current is passed through this wounded wire As a result, we get magnetic field produced nearby it. And here also you have an insulated wire wound around an iron core, and when current flows through this arrangement, we get magnetic field around this setup. This you call it as an electromagnet. So we are producing magnetism by passing an electric current. We can increase the magnetic field by increasing the current. That is one way of doing it. So we can increase the magnetic field produced by increasing the current flowing through the insulated wire. The second one is by keeping the current constant, we can increase the number of turns of this wire. As a result, a magnetic field increases. This is because of the superposition principle. What is superposition principle? The magnetic field produced by each turn of the coil gets added up, and we get a large magnetic field. So if we increase the number of turns of the coil of the wire that is wound around a solid core, this is an iron core, that solid iron core, and we can increase the magnetic field produced here. This is shown in this diagram. For the same 6-volt battery, we have fewer number of turns or lesser number of turns, so we get a weaker electromagnet. For the same 6-volt battery, which means the same current flows through the wire, but if we increase the number of turns, we get a stronger electromagnet. Therefore, the magnetic field produced around this is very much stronger when compared to this case. Now we see what is a solenoid. A long wire that has been wound many times in a tight coil around a hollow or a solid core is called as a solenoid. A long wire that has to be wound many times. So this is the arrangement. A long wire that has been wound many times. Right? This is a helix or helical in shape, right? Whereas the electromagnet can be wound in any shape. For example, here it is the horseshoe type. But whereas solenoid cannot be in that shape. The solenoid has to be in a helical shape. The core can be air or a solid iron core, right? So a wire tightly wound many times around a hollow core, air core, or a solid metallic iron core. We call it as a solenoid. Here the magnetic field produced by the solenoid is uniform inside the core, right? Inside the solenoid. The magnetic field of the solenoid is due to the superposition of the magnetic fields of each turn of the solenoid, as we have seen earlier. So we have to add the magnetic field that is produced by each turn of the coil of the wire, right? Now we can also find out the direction of the magnetic field that is produced, where the north pole will be, where the south pole will be, by once again using our right hand. If we curl all the rest of our fingers towards the direction of the current, then the thumb of our right hand will always point towards the north pole of the magnet. This is how we can determine the direction of the magnetic field produced by a solenoid also. Then uses of an electromagnet. In the first diagram, we have a garbage removing crane, right? In this crane, once the crane is started, then the current from the crane of the battery flows to the coil of the wire. As a result, the coil of the wire produces a magnetic field around it, which picks up the iron filings and iron pieces from the garbage separately. So this is a remarkable invention. Another one is here you have a speaker. In the speaker also you have a coil of wire, and when current flows through the coil of wire, it produces a magnetic effect. You have a washing machine, you have an electric fan, all of them you have a coil of wire. When current flows through the coil of the wire, magnetic field is produced. As a result, it gets turning effect. It gives a turning effect. As a result, our washing machine revolves and our electric fan revolves. This is an electric bell. The detailed description of an electric bell and how it works will be provided in my next video. So now we go to the summary. In this video, we have discussed what you mean by electromagnetism, that is the magnetic effect of an electric current. What do you mean by an electromagnet? What is the difference between an electromagnet and a solenoid? How to use the right hand thumb rule to determine the direction of the current, and the uses of the electromagnets. I hope you enjoyed this video. Kindly like and share this video among your friends. Thank you.